What happens to an X-ray machine over time and why the image deteriorates? Today, I'm going to show you all this cool equipment and what is the impact they have in the quality of your X-ray machine. It's well known that over time, the image quality of X-ray machine is going to degrade. So in this video, we're going to go over why it happens and how it happens. What are the tools that we can use to measure that degradation so that you can understand at which point you should do something about it, right? Either recalibration or replacement of some critical part. So let's start with the three pieces of an X-ray machine. The actuation, right? How things move inside of X-ray machine, the X, Y, Z tilt, X-ray source, and X-ray sensor. The actuator, the first one, is pretty straightforward. Over time, the gears, the belts, if they have any belts, will deteriorate, but those are fairly straightforward to detect and fix, right? If you keep your system properly lubricated and if you do the yearly maintenance or preventive maintenance on the machine, that should be pretty straightforward and you shouldn't have to worry about actuators failing or having any issues, especially related to image quality, right? You're going to be fine. Now, let's talk about the X-ray detector because that's, the flat panels nowadays are designed to be able to withstand a much higher radiation dose than they were just 10 years ago. So what happens is, as the detector takes on radiation, the transistors inside, because remember the X-ray detector, X-ray sensor is basically a bunch of transistors that are used for the preamp of each pixel that is going to capture the signal coming from the scintillator, and then a tiny little signal from the scintillator is going to be amplified, and eventually that analog signal is going to be moved to the digital space through an A to D converter, ADC, analog to digital converter, and then that digital signal is going to be sent to the computer, and eventually that pixel digital information is going to become an image that you see in your computer monitor. So what happens is that those preamps, all those things are designed, basically a collection of transistors, and as the radiation accumulates on those transistors, the base of the transistor gets a little noisier every time. So what you're going to see is that as the detector ages, as the detector gets more and more radiation, it's going to get grainier, right? It's like this white noise grain that's going to be populating the whole detector. And depending on the distribution of radiation on the detector, you might see areas of the detector that would degrade faster than others, right? And there's some things you can do to mitigate that with filtering and some level of averaging of those pixels to, wash out some of the white noise, but eventually the detector is going to degrade to the point where it needs to be replaced. What happens sometimes as well on the detector is that you might have a failure of a whole column or whole row of pixels, and you end up with a black line in your image. That means that the whole row has been damaged. Properly, the accumulator, that the machine that reads that row of pixels is going to get damaged, and you lose a whole pixel or a whole column, depending on how your detector is arranged. So, actuator, not a huge impact or no impact on image quality. Sensor, again, flat panels today are designed to last well over a decade and are very resilient to radiation. So let's go to our third component, which is the X-ray source, the generator. So I have some examples right here on the table to show you how these things are built. This is an old X-ray tube that we got from our shoe scanning machines, and we have some cool videos on that, so don't forget to check it out after you finish watching this video, of course. And what you see here is the filament inside this cavity, and the filament is where the electrons are generated. The electrons are then accelerated from the filament towards the target, and at the target, they hit the tungsten element on the target, which then, through that brainstorm radiation, and we've talked about this before, you can go some other videos to check it out, but on that target, that's where, when the electrons recoil back to their shell, that X-ray photon is emitted out of the tube into the air and towards the sample. Now, what happens is, after you use this for many hundreds and hundreds of hours, that filament is hitting those electrons at the same location on the X-ray tube. And as you keep hitting, we keep banging the target on the same location over and over again, we create these little holes. Because remember, at that location where those electron beam hits, the tungsten gets really hot. So you create, and as you can see here, little imperfections on the target. And those imperfections over time create these cavities on the target that will make those X-ray photons, instead of going in one direction, they start getting in different directions that you can't really foresee. And as a result, over time, the resolution of your image, right? So instead of having a sharp edge of your image is going to get fuzzier and fuzzier and fuzzier. Now, the damage on the target is a function of how much current, how many electrons you're hitting the target with, right? So that's the power of X-ray tube. Now, the more powerful the X-ray tube, the more current you're going to put, and the more electrons you're going to get on that filament, the hotter that target is going to look, and the faster the damage is going to happen. So for high power tube like this one that I have here, we have what's called rotating anode. So as you can see here, so in this example, for applications that require really high power X-ray tube, meaning that you need a lot of current on the filament, meaning you need a lot of flow of X-ray photons coming out of your tube. But what we do is we design this rotating anode. So instead of the electron beam hitting one point on the target, what we do is we keep rotating the target, so a new target location is presented, right? And as then it gives the other locations time to recover, cool down before they get hit by an electron beam again. So very cool development, which allows us to achieve much higher filament currents without destroying the target quickly. And here's another view of the same target. As you can see, it rotates really nice, and even with this rotation, after a few thousand hours of use, you can see this striation, those lines on the target, which represents the location where the electron beam is hitting the target to create X-ray photons. So again, this will happen over thousands of hours, right? And the X-ray source will slowly degrade, and the image is going to get, the resolution is going to degrade over time, ever so slightly. And to be able to keep up with the status of, and again, this is why it happens. So how are you going to figure that out? How are you going to measure quantitatively, right, in a quantitative way, what is the resolution of your X-ray machine? And for that, we have a set of what's called IQIs, image quality indicators. Image quality indicators like this one, we have line 1 from STM, we have line pair gauges, we have step wedge. These IQIs allow you to take a snapshot of the status of the X-ray tube, your sensor, in this point in time. So you have a reference image of your resolution and the power of your X-ray tube, right? For example, you know that at 90 kV with this much exposure and in this location of the histogram, this step gauges give you an area on the detector with a grayscale of, let's say, 100. A year from now, 2 years from now, 10 years from now, you can take that same image and see, instead of 100 number on the ADC, maybe now you have 90. So you know that the X-ray source over time got a little bit weaker, right? That target's not as sharp anymore. And that's how we measure it with these step gauges. You can check the resolution of your X-ray tube using what's called line pair gauges. So this gauge has a set of lines that run not parallel to each other, they run near each other at ever approaching distances, and how many line pairs per millimeter is given the scale here. So you can place this unit, this plate on your X-ray machine, and you can see, for example, 10 line pairs per millimeter. Over time, that resolution is going to deteriorate, and you can say, okay, the minimum resolution that I can accept in my analysis, 5 line pair per millimeter. So you are at 10, the lowest resolution you can afford is 5. And over time, you can keep measuring year after year on X-ray use. And when it hits 5, you know what? That's time where the X-ray source needs to be replaced because it have achieved the lifetime of resolution that this X-ray source is able to give me. So I hope this video has been useful so that we understand how the X-ray, the quality of an X-ray machine is measured, and what are the components that play a role in the deterioration of these images over time. And again, if you have any questions, please give us a call. And if you have any suggestions or videos in the future, same thing, reach out to us at creativeelectron.com, and don't forget to subscribe. Thanks for watching.